I'd like to just do a quick review of output mapping before moving on to input mapping. So here in the graphics formatter, I've got LA is numbers 1 to 6, number of columns is 6, there are 6 cell formats there, and I've got mappings, output mappings, defined here in cell text in the following way. Now, I'll press equals and you can see what happens. Now, first of all, that's how we showed it before, equals 1 colon hello, exactly the same as we saw before. You can also use a space instead of a colon, so equals 2 space world, and that's fine. You can also, if it's equals, leave out the if it's equals, you can leave out the equal sign. So you can just put 3 maps to no, 4 maps to never, 5 maps to no text. When it comes to greater or equal, you have to leave that in. So greater or equals to 6 maps to bye-bye. Now, that's what we see there. The only difference is from something we haven't seen before are these two codes here, 190503, and those codes request that the text should be a larger scale and not in a text box, just put into the cell. So here 19 means large text, 05 means it should have a foreground color that's blue, and 03 means it's going to have a red background. And that's what we end up with there. Do note though that the word never, half of it's missing, and that's because you can really, with that large text, only squeeze in 1 or 2 characters. I now want to look at input mapping, where text or symbols can be mapped to individual numbers in any input field. This is done in the mappings area up here, and essentially what you do there is you specify pairs of text and numbers. So you might say, for example, that white will map to 1, black will map to 2, red will map to 3, green will map to 4, and blue will map to 5. Just to show that these are treated like any number, I can go up to here and I could choose to add the word red plus blue, and red was 3, blue was 5, so I get the number 8 as the answer. Let's be honest, that doesn't seem very useful, but we could go up to row G and we could say, instead of saying, as we have done before, generate 100 number 3s, we could put 100 red. And now when we come down to the animation zone, change it to size 10 and put G1 in here as our input, we will get red. I'm going to clear this and then show you something that is more useful, which is to come up here and use mappings to allow us to enter word lists, for example. And we do that by pressing this number here, or this little button, A to Z, and that maps A to -1, B to -2, and so on through to Z to -26. So now what we can do is we can go up here in E1 and we can enter some words. Instead of writing numbers in here, now we can write A, P, P, L, E. We still have to separate them because they are still numbers. R, A, V, E, N, and C, H, I, M, P, And so now we've entered 3 what to us look like words. We come down here, and if we make E1 the input to this, and we make the number of columns 5, then, and we press equals, we get the numbers that they map to, -1s, -16, -16, and so on. Now, of course, if this were a word and letter game, we wouldn't want to see -1, -16, we want to see AP. So we need output mapping to allow us to do this. So, output mapping is down here, just below here. So we could put in here a special word called mappings. And if you put that word in there, instead of defining individual mappings, you can just say, take whatever is in the mappings area and reverse them. So it's like having in here -1 goes to A, -2 is mapped to B, and so on. So now if we press equals, we now get those letters. Okay? To make the whole thing look better, we could come up to here and generate, what have we got there? 15 letters, and we'll make it 190506. So we've got 15 codes there, and if we put those in as the cell formats, by the way, what you see here is what you get if you don't have any cell formats defined, just white text field on a white background. So if I put in here G1 and press equals, now I get much nicer looking output. You need to be aware that there are some words you can't map from. You can't, for example, use any of these numbers here or these words here, pi, e, asterisk, which is the base of natural logarithms, the word click, keypad, they all have internal value meanings, special meanings, L0, which is the empty list, or the word now, because that is a list that has a lot of information about the current date and time. So it starts off with date format such as 2024, 10, 11, then year 2024, and so on down to milliseconds. You also can't map to any word that might be a reference name. For example, A1, B1, Z1, form 1 here, equation 1, because they have already got meanings defined. I'd now like to look at arithmetic in Numipulator. Now, we have the number operations in row A and the number functions in B, and their item by item equivalents in rows V and W. They provide basic arithmetic, but only one operation or function at a time. Joining several of these together to carry out more complex calculations is perfectly feasible, but it is tedious. So the ability to solve more complex expressions is provided in quite a surprising place, really, in row C, list function to number. There are two functions here, calculator and expression, that can be used. In both cases, the basic idea is that the list of numbers that is the input represents a sequence of number, operator code, number, operator code, number, and so on, ending with number. The operator codes are 1 means add, 2 means subtract, 3 means multiply, 4 means divide, and so on. These are all specified up here, if we go to codes and we look at number operations further down, we will see them here. They're all defined, those are the functions, and here are the number operations. So let's try this out here. Let's choose the calculator expression here, and we'll use expression here so that we can see the difference. And we'll put in 2, 1, 4, 3, 5. So that is where 1 represents plus and 3 represents multiplied. Put that in both of them, and we'll do equals, and we get different answers. Clearly it's done some sort of calculation, but they're different, and that's because in the calculator the calculation is done very simply from left to right. So it's 2 plus 4, which is 6, times then 5, which is 30, as opposed to with the expression where normal operator precedence is used. In other words, multiplication is done before addition. So here this means 2 plus 4 times 5. So it's 2 plus 20, which is 22. Now there are also functions to consider, and we'll just go a bit further down again and you look at the function codes. And we can see those here. 1 is square, 2 is square root, 3 is plus minus, and so on there. Now clearly with a function we can't just use the same idea of having number operator, not if we just consider functions. So what we do instead is we use a mock operator function. So if we have here, for example, 2 plus 4, which is 6, if I put 100 in there, that's a mock operator one to indicate that the next thing is going to be a function. So if I put in 1 there and do calculate, I get 2 plus 4, and then it's squared because the 1 means squared. So that's how we use functions within these expressions. So we can use lists of numbers to carry out quite long expressions if we wish to, but it's not very readable. So if we go down here, what I've done is I've pressed this button here, which is plus, minus, times, divide, and that puts in mappings from, for example, plus meaning 1, minus 2, little x, 3, divide, /4, and so on, including, as we'll see later, and or, and also less than, greater than, and so on down here. So there's quite a lot of mapping there. So if we now come back up, we can come here, and instead of having 2, 1, 4, we can put 2 plus 4, and now let's do it on this one here, 2 plus 4, and times there, and now we do that equals, and we get the same answer when we press it. 22 there, 36 there. I haven't yet done any mapping for the functions here. I will deal with the functions now. I'll go down here and I will add in here func maps to 100, and square maps to 1, and root maps to 2. We could add in whatever functions we wanted to there. And now we can come back up here and we can now put function square and equals, and we do get the answer 36. I would probably put for emphasis, I would put a colon in there to make it clear that that's sort of related to each other. 2 plus 4 function square equals. Let's just make sure that's really working. Change that to 2 plus 6 function square. And we get 8 squared, 64. I'd like to move on from simple arithmetic to logic and comparisons. So if we move up to number operations here, you will find that there are checks here. For example, we might have check that A is less than B. We might have here logic A and B, and we might have logic A or B. Now in all cases, the 1, 0 in the middle there means that the response, the result, will be either 1 if it's true or 0 if it's untrue. So if we say here is 2 less than 3 equals, and the answer is 1, whereas if we say 4 less than 3, the answer is 0. Now we've already got mappings from words to all of our number operations, so we can start to use these in these expressions, including the comparisons and the logic. So if I put in here an expression, I've already typed this in somewhere just so you can see it a bit better, and you would normally use the expression here because you want to get the arithmetic evaluated before the comparisons, and the comparisons before all the ands and ors. Now we press equals. Oh no, we need to put in some values here. 3 and 6 and 8 for D1, D2, D3, and equals. And now we get that that expression is true, or 1, evaluates to 1. There is also a not function found under the number functions, which outputs to 1 if the input is 0, or 1 if it is not 0. And that can be treated like any other number function. Note that with these expressions, there is no equivalent of parentheses or round brackets to change the order in which the calculations and so on are carried out. This means that you may need to combine 2 or more expressions to achieve your desired result. Remember though that if you want to evaluate brackets 2 plus 3, then close brackets times 5, rather than 2 plus 3 times 5 in brackets, you can get this result by using the calculator function rather than the expression function. And another thing with these is don't forget to leave spaces between the numbers and the operators. We'll just refresh this to straighten up those boxes. And now we'll go to row H, where there are a couple more things like calculator, except this is called there's one called calculator list and one called expression list. Now these are very similar to the last one that we looked at, except that it can produce more than one result. The input is again number, operator, number, and so on. But if a 0 is found where an operator is expected, this is treated as a separation of expressions to be evaluated. So 2 times 3, 0, 4 plus 7 gives the result 6, 11. Let's try that. So if we go here, 2 times 3, 0, 4 plus 7, then we get the answer 6, 11. If we look down at the mappings, we can see that the word next has been mapped to 0. So this allows us here to replace the word 0 with next. Just to remind yourselves that this is something a bit different, and we'll get the same response, same answer. And the same would be true, that's calculator expressions, the same would be true of expression evaluation. I'm going to move down to the last of the if-then-else expressions, and you may notice that by default they are all set to if expression LA equals LB, then LC, else LD. So what this is about is we can put one of these expression lists into LA. So we might put in what we put in before, which was something like that, just a single expression to be evaluated. And we want to say if that is true, and we'll just put in 1 there to represent the fact that it's true, then the answer is 21, 25. Otherwise the answer is 9. And so we evaluate this and we get the answer 21, 25, because we found before that that expression does evaluate to true. If we put in 0 there, we would get the answer 9. Now we can put in another expression. For example, we might say next if 5 is less than 7. You're not likely to put this in, but it's just to check. And so if we put in, this time we'd have to put in 1, 0. Let's put in 1, 0, and we get the answer 9. That's because what we're saying here is this expression evaluates to 1. This expression evaluates to 1 as well. So that is not equal to 1, 0. It is in fact equal to 1, 1. So if we put in 1, 1, we will get 21, 25. So this enables us to put pretty complex expressions in our if-then-else expressions and to get lists as a result. Just like to cover one other use of input mappings for operators, and again that's in this row, row C, and you'll find there's also a number of things here called, for example, beginning with case. Now let's just try a simple one here, case equals. Now case equals says, let's look at D1 there. D1 is equal to 3, so we can say here if, basically this is saying if D1 is equal to 5, then the result will be 24. If D1 is equal to 3, then the result is 25. Otherwise, we can put a default here, it's 26. So we would expect the answer to be 25, and it is, because D1 equals 3, so it matches that, so that's the answer. Now, there's also a more general one that allows you not to have the same operator throughout, called case complex, and this would allow us to say things like if D1 is greater than 5, then the answer is 24. If D1 is less than or equal to 6, then the answer is 25. And then default will be 27. And again we get the answer 25 because D1 isn't greater than 5, but it is less or equal to 6, so we get the answer 25. Case comp actually relies on having operator codes in the second position here, so where we put the greater than or the less than or equals, I could have put there, I think it would be 19, and that one would be 15, something like that. But the point is, once you've defined those mappings down in mappings from symbols to numbers, you don't really need to worry about the number codes anymore for the operators. Now we're going to look at standalone apps. So when you've created an app that you're happy with, you can make it available for others as a standalone browser app. That is, it's an HTML page that can be opened and run in a web browser. You can send it to friends or put a link to it on a website, for example. We'll demonstrate how to do this with one of our own built-in apps, Alien Invasion, which, as you can see, we've already got loaded into Numipulator. First, you go down here to Input Outputs, and you select Create Numiplet. You need to select all of the text that's created here. Let's just have a brief look at it. You can see your description there, and there are all the definitions, the whole of the program and all the settings wrapped up as text. And so we select it all and copy it, and now we're ready to open up the standalone app maker. You'll find the standalone app maker on the numipulator.com website. It's down near the bottom, and you've got the Numipulator standalone maker app. So we open that up, and now you see it tells you to, if you read that, it says paste in the code. That's the code we've just copied. Paste it into there and create the app, and that creates a complete the code for a complete web page. Again, we need to copy that, Control-All, Control-C, and copy that, paste it into a text file and save it as whatever you like, maybe alieninvasion.html, and then you can open it up. I'm now loading Alien Invasion Demo. That's what I saved it as, alieninvasiondemo.html, and it opens it up and I can start playing with it. And there we go. Can we shoot any down? Yes, we can start shooting some of them down. Now what you see here is you don't see the complete Numipulator package, but actually it's there, but most of it's hidden. The only things you really see here are the animation zone, the description down here, the feedback up here, which includes the score, and of course the keypad here. Oh, and a few buttons over here to start, go, and stop. Just a few words to conclude this look at Numipulator. You may have noticed, if you're familiar with other programming languages, that there are no statements concerned with doing things such as printing, and there are no variables that can be used to store values at any time. Numipulator is what is known as a declarative language, as opposed to a procedural language. The core language for calculation and manipulation of numbers is concerned with specifications for outputs. There are, of course, procedural aspects concerned with Numipulator programming, namely output display, repetition control, delay between cycles, and deciding whether or not to display graphics between cycles. However, the programming for all of these is declarative, determined through explicit settings or calculation, or implicit defaults. This makes Numipulator 100% declarative environment and language, which is quite rare. Most languages that are classed as declarative provide explicit procedural support. For example, in the language Prolog, you have cut and print that can be employed anywhere within the program execution. Numipulator doesn't have this or allow it. Numipulator, in contrast, performs pure calculations and manipulations. Most are true functions, but some, such as random number generation and list permutation, are not, but are still specified declaratively. The procedural aspects of program execution can be influenced by specifying values associated with these only, not by writing procedural statements. I did just want to mention, lastly, one thing about a Numipulator program, which is it's not that easy to read everything, particularly when you've got long lists of things, such as down here. But if you press the text button up here, then you will get the whole program laid out in a more readable style. So if we go down here, you can see there's E1, it's got initial board values, E2, board colors and actions there, and so on all the way down to the bottom. Much more readable. Overall, Numipulator is not a general purpose language. Rather, it is focused on allowing the rapid development of simple to moderately complex games and puzzles. We hope you enjoy programming with Numipulator, and do tell your friends, colleagues and family and other contacts about it.